the end that I'll mention, with Louisa Lyles and Xiao Lo, who are currently graduate students here at Virginia, graduating soon. And let me start by giving a little bit of background. This research direction was started by Von Jones about 10 years ago. And he was really motivated by the question of approximating various objects in conformal field theory by discrete lattice models. This is not kind of the subject of my talk, but this is the kind of the background and motivation. And as part of that, if you have some kind of a two-dimensional region in the plane, like a disk, say a disk, then the diffeomorphisms of the circle that act on the boundary. And there is a well-known kind of discrete version of this, which is the Thompson's group, not F, but T actually, which is the group of piecewise linear diffeomorphisms of the circle with some particular slopes. So this is kind of the background for how I believe he started thinking about the Thompson's groups. So there are several versions of this Thompson group, and I'll focus on Thompson group F, which is also kind of most of the context for Von Jones's work as well. And as part of this work, he constructed unitary representations of the Thompson groups, group F, and he also showed how to construct links in 3-space starting from elements of the Thompson group. And in a couple of his papers, he suggested that, classically break groups have been used to generate links, knots and links in 3-space, and he suggested that the Thompson group is kind of a new candidate for this role for generating knots and links in 3-space. So I'm going to recall all these notions and then discuss new work. So this version of the Thompson's group is the group F, and these are piecewise linear orientation preserving homeomorphisms of the unit interval. And I'll have some examples in a minute, such that all derivatives, all the slopes are powers of 2, and all points, which are kind of corners of these straight line intervals, are dyadic integers, dyadic numbers. So they're numbers where you have an integer divided by a power of 2. Okay, and so one way to encode Thompson group F is using 2 standard dyadic partitions. And subintervals in these partitions are going to be where the function is linear, and the ends of the subinterval is where there's some kind of a change of slope. So the subintervals of a standard dyadic partitions are of this form. It's an integer divided by a power of 2, and then this integer plus 1 divided by the same power of 2. Okay, and so given a pair of such standard dyadic partitions with the same number of subintervals, there is a unique element of this Thompson group F such that the image of it takes the first standard dyadic partition to the second one. So here is an example. We have the following piecewise linear homeomorphism of the interval. In this case, there are sort of 3 points where it's not linear, 2 points where it's not linear, and then there are 2 endpoints. And you can encode these partitions by planar binary rooted trees, where whenever you divide your interval into 2 halves, you have a split in your tree. So in this case, the way that this tree is generated, like there is a point, there's a 1/2, you divide the interval in 1/2, and this is the first split of the tree. And then there's a second split in this first dyadic partition, and you have the second kind of split in your tree. And so this standard dyadic partition encodes the domain of this homeomorphism, and then the second standard dyadic partition, in this case, encodes the kind of the range, the codomain of this map. And one way to encode this element of the Thompson group is just to glue these two trees together. So this is kind of a standard representation in the subject, and von Jones used this, but it dates back before that. This sort of in a geometric study of elements of the Thompson group. So this is a way to think about the elements of the Thompson group is using two trees of this type that are glued together like this. Okay, well, this is not a unique representation of this piecewise linear homeomorphism. One way to change it is to do sort of a refinement. So in this case, we can take, so going back here, we can look at the leftmost subinterval in both of them and just subdivide it in half. And so this is what is represented by a red dot here. In both of these static partitions on the left subinterval, we just divide it in half. And it represents exactly the same homeomorphism, but it's a different pair of trees. And the difference from the previous pair of trees is that we have this kind of bubble born here. And this bubble has a name, it's called a canceling caret in this pair of trees. And so we'll declare that two pairs of trees are equivalent if they differ by these a finite number of these canceling carets. And a pair of trees called reduced if you cannot cancel it. So there are no canceling carets. And then it's a sort of a theorem that the elements of the Thompson's group F are in bijection with reduced pairs of planar rooted binary trees. Okay, well, so one of the ideas of Jones about 10 years ago is that you can create links in the following way. So if you go back to this pairs of trees, there's a sequence of splits and merges. So usually we kind of read from top to the bottom. And so these vertices over here are called splits as you go down. And then there are merges where kind of two strands of a tree come together. And so the construction is that whenever you have a split, like on the upper left part of the picture, you add a new edge, which is drawn red. You get a 4-valent vertex, and then you represent the crossing in the following way, so that the horizontal strand is always on top and the vertical strand is kind of behind it. And then exactly the same prescription is also applied for merges, where you again add a red edge to make it 4-valent, and then you resolve a crossing so that you get a sort of a tangle, and the horizontal strand is always on top. And so here's an example of a knot or a link that you generate in this way. In this case, it's I believe an unknot. So if you start with the Thompson group element that corresponds to this pair of trees on the left, then at each merge and at each split you implement the prescription that's described above, and then you get this unknot. It just happens to be a knot in this case on the right. There are these additional strands that are drawn red, but this is just for convenience to see sort of, in each of these regions in the plane, you add one of these red strands just to make it 4-valent and so on. But at the end of the day, there is nothing special about them. They don't have to be red on the right. So you just get a link. Okay, so this is the review of Jones's construction. And in that paper in 2014, Jones also proves kind of the Alexander type theorem that every link in 3 space is realized by this construction. So there exists a element of the Thompson group that creates that link. What is unknown is kind of the analog of the Markov theorem for Bray groups. It is unknown what a set of Markov moves is. It's definitely true that many different group elements give rise to the same link type, but it's unknown what the precise set of Markov moves is. So this is to be constructed with a theorem that we're going to prove for tangles that I'm going to describe in just a couple of minutes. Okay, so now let me move on and discuss strand diagrams. And this is a different representation of elements of the Thompson group, and this is due to Belk and Matucci in the mid 2000s. So this is a more general diagrammatic object than just a pair of trees. And so what we have here is an MN strand diagram where we have M kind of endpoints on the top of a rectangle, N points at the bottom of the rectangle, endpoints at the bottom of the rectangle, and then each point in the interior. So I did not draw a rectangle here, but it's kind of to be imagined. And each point in the interior of the rectangle is either a split or a merge. And again, we're going to go down in a vertical coordinate, and so there are splits. So here is a split, and there are also merges. And the edges have non-zero slope. This is just a convenient convention. So this is sort of the analogs of tangles, but in this combinatorial world of strand diagrams. And I'll explain the relation to the Thompson group in just a minute. So let me just mention one more thing, that if you wanted to think about pairs of trees, this will be a 1-1 strand diagram. If there is a single point on the top and a single point on the bottom, then this reduces to the previous discussion of pairs of trees. This is just a generalization to more points on the top and the bottom. And there are two local moves that are relevant in this context. And again, I'm describing this work of Belk and Matucci. The first move was already seen for pairs of trees. This is canceling carrots. The second move actually does not happen for pairs of trees, because you'll never find this configuration for a pair of trees, but it does obviously happen for strand diagrams. And so we'll consider two strand diagrams equivalent if they're related by one of these two, by a finite sequence of such moves. And if you cannot go from left to right, then this is going to be called a reduced strand diagram. And reduced strand diagrams form a group where if you have two strand diagrams, and I'll have examples in just a minute, you can stack them. This is just like multiplication of tangles or multiplication in the temporal Lie algebra. So you stack them vertically, and then typically it's not going to be reduced. So you reduce it using these two moves, and you end up in this group again. And so this is a multiplication. There is the inverse, where you just take a strand diagram and you just turn it upside down. It turns out that this is the inverse. You can prove that using these local moves, and then the identity element is just the vertical and vertical strands. So it turns out that, and again, I'm still summarizing the work of Belk and Matucci, that the R11, which is the group generated by reduced strand diagrams with 1 point on the top and 1 point at the bottom, is isomorphic to the same group, but with actually any number of n points on the top and the bottom. In this case, it's convenient for us to consider a special case where there are 2 to the n at the top and the bottom. So let me explain how this works. So on the left-hand side, so this is an element of R11. So there is a single point on the top and the bottom, and this is just an example, a pair of trees. And the way to get from this to, in this case, n equals 2, this is just an illustration, but you can get to any n. We can just multiply it by a tree on the top. In this case, it's a symmetric tree. So I'm just taking this tree with 4 leaves on the top, and then I'm taking the exact same tree, but reflected at the bottom. So I'm essentially conjugating by this tree. And then you can use the local moves. Recall that whenever you see a configuration like this, then this is equivalent to just 2 vertical strands. So you can start using this local relation, for example, over here and over here. And then after you do this, you find some more places to use this. And you realize after all these manipulations that in this example, you get a diagram on the right. You can simplify it. This is an isomorphism because you can also go back by conjugating by the inverse of that tree. So if you wanted to go back to a pair of trees, you can actually multiply by the inverses of the trees on the top and the bottom. And then you can cancel these using the same local moves. You can start simplifying, and you just end up with the same pair of trees on the left. So this is an isomorphism. And this is not kind of the usual isomorphism. We're using the symmetric tree. I think typically in the subject they use they call it a right vine to relate the piecewise linear homeomorphism of the interval to piecewise linear homeomorphisms of the half line. But for our purposes that I'll explain in just a minute, it's more convenient to use the symmetric tree so that we end up with strand diagrams with 2 to the n points on the top and the bottom. So this is sort of a very useful observation. And the corollary of this is that the Thompson group F is isomorphic to this group generated by reduced strand diagrams with 2 to the n points at the top and the bottom for any n. So you can start with a pair of trees. You can start with a Thompson group element and represent it as a reduced pair of trees. You can also, kind of like on the left here, but you can also represent it as a reduced strand diagram with 4 points on the top and the bottom, or 8 points, or any number of points, any power of 2 that you like. Okay, and so we're going to use this to associate tangles with elements of the Thompson group. And so we are taking the same local picture as Jones did. So near each merge and split, we add a red fourth edge, and then we resolve this 4-valent vertex into a crossing where the horizontal line is always on top. And well, in this case, there is a little bit more combinatorics, and you have to prove a lemma, which is correct, that if you look at any bounded region in the strand diagram, there is a unique maximum and minimum. And then this red edge that we're adding is going to connect this unique maximum and minimum in each of these planar regions. There are also these unbounded regions, and you just kind of introduce a midpoint at the top and the bottom. And anyway, if you go through this process, you get to a tangle. So we start with a strand diagram on the left, and we end up with a tangle on the right. So this is a generalization of the Jones construction, where instead of, so he started with the element of the Thompson group, and he constructed the kind of a closed link in 3 space. And we can start with a element of the Thompson group F and end up with a tangle where the number of endpoints on the tangle corresponds to the end, which is, on the previous screen, we choose any n we want, and then we work with strand diagrams with 2 to the n points on the top and the bottom, and then we construct this tangle. So we prove an asymptotic faithfulness result, saying that if you have 2 different group elements in this Thompson group F, then for sufficiently large K, if you go through this process, so you associate a reduced strand diagrams with 2 to the K points at the top and the bottom, and then, okay, this is the theta sub K, and then you can look at the tangles associated with them, just as described on the previous screen, and they're going to be non-isotopic. So this is to be constructed with the Jones's construction, where contrasted with the Jones's construction, where there are lots of different group elements that give rise to the same link type. In this case, we show that if you go to Tangles, then for sufficiently large K, it's actually asymptotically faithful. Okay, the reason why we were interested, one of the reasons we were interested in this was to kind of apply link homology. And so this is, let me describe this application. If you would like to study Havanov homology, then typically you have to work with oriented links. And so this is kind of the next topic. And again, there's going back to the work of Jones, there is a subgroup which he called the oriented Thompson group. And so this is a subgroup, which is usually denoted as F vect, which is a subgroup of the Thompson group F, which consists of, there are a couple of different equivalent definitions. One of them is that this is the set of all elements of the group F, so that when you go through his construction, you get the link diagram that bounds an orientable checkerboard colored surface. So in this case, this is the pair of trees that we started with on the left. As you go through his construction, you get this link diagram, and then there is kind of a natural checkerboard colored surface you can draw there, and it's orientable. And so this is an example of an element of the oriented subgroup. Okay, well, there is a version of the Alexander theorem also due to Aiello in 2018 that if you start with any oriented link in 3-space, then you can build it from an element of this oriented subgroup of the Thompson group as well. Okay, so there is some work that we use of Aiello, Conti, and Jones, and we extend this to Tangles. So we define the notion of an oriented strand diagram, and we use it to construct oriented tangles. And so this version is that an orientation on the strand diagram is an assignment of signs, pluses and minuses, and the complement of the strand diagram in the rectangle where it's drawn. And locally, it has to be one of these 4 configurations. And a strand diagram is called orientable if it admits an orientation, so that at each vertex is one of these 4 types. If you have an oriented strand diagram, like what is drawn on the left, then there's a version of sort of the Jones's construction where locally you replace it. Again, you add a red strand to make it 4-valent, and then you resolve a 4-valent vertex into an over and under crossing where the horizontal strand is on top, and you get an oriented tangle. And so this is just a kind of an oriented version of going from the Thompson group F to 2 to the n to the n tangles, which are oriented. Okay, and so our goal here was to study sort of link homology version of this, and the background or motivation for this is that link homology is kind of in this general 3+1 dimensional TQFT context. So there is a Higard-Floyer homology, and there is a watered version of that, where mapping class, there is a kind of an action of the mapping class group on the water theory in Higard-Floyer. And in the Havanov context, there's an action of braid groups on the triangulated category of Havanov chain complexes, homotopy category of Havanov chain complexes. So we wanted to kind of study the analog of that for the Thompson group and kind of extend this analogy that Jones suggested, that instead of braid groups, we can use Thompson group. And Jones used the Thompson group to generate links, but perhaps you can extend this and maybe you can generate 3 manifolds and so on. So we just wanted to extend this analogy. And to formulate this notion of a group action that works in this context, there are two bicategories. So these are sometimes called weak two categories. And the first one is, this is just a way to formulate a group action. In our case, is going to be a lax group action of this group, which is the Thompson group on the sort of irrelevant category. So to make this precise, if you start with a group, you can define this bicategory where there's a single object, which you can think of as just a star, and then there's a morphism for every element of the group. So you can kind of think of them as acting like this. And the composition of morphism just corresponds to the multiplication in the group, in this case, the Thompson group. And then two morphisms are trivial. Okay, and then the other category is the two-category cat, which is kind of a standard thing that people consider here. And the objects are small categories, morphisms of functors, and two morphisms of natural transformations between functors. All right, then if you want to define a group action on the category, whether it's a genuine group action or in our case, it's going to be a lax group action, it's going to be a functor from this category star sub G to the category cat, so that P of this unique object is this category C. So we're trying to act by group on a category C, and the unique object in star G goes to this category C. Then group elements act as functors in this category, and then, well, two morphisms become natural transformations. But so in our case, this group action is going to be lax. So let me, the entire definition is quite involved, but there are kind of two key things that I'd like to focus on, and then there's a kind of a key axiom that has to be satisfied. So there are the two key pieces of data are these functors that correspond to group elements. So for each group element in your group G, you should have a functor acting on your category C. And then whenever two group elements are multiplied, so it's H times G, there should be a natural transformation from the composition of these two functors, PH composed with PG. There should be a natural transformation to the functor which corresponds to H times G. And okay, and then the axiom that should be satisfied is kind of the associativity. So if you have three group elements, then you can multiply them on the left or on the right, and then kind of group them, and this diagram should commute no matter how you're going to group the multiplication. And the difference from the genuine group action is that these natural transformations, T sub HG, they don't have to be natural isomorphisms. And we'll see in a minute why this is true in our context. I also want to point out that this is not a kind of a new definition. In the Higard-Floyer-Water theory, there is also a version of this. It has a slightly different name, but the action of the mapping class group there is also has some feature of this lax group action. Okay, well, so how is this constructed, and what is the category that we're going to act on, and what are these functors and natural transformations? Well, so let me recall that this is the Khovanov's tangle theory. There is a Khovanov ring HN, which is defined using essentially kind of the temporally flat tangles. And so it's kind of a beautiful theory that was due to Khovanov in the early 2000s. And as part of that, if you have not just a planar tangle, but any MN tangle, you associate to it a chain complex of geometric bimodules. So, so if you have, some sort of tangle for like here, so here's a easy example, then you can resolve the crossings just like as usual in Havana theory. And then once you resolve the crossings, you get flat tangles. And the definition of the geometric bimodule is that a bimodule is geometric if it comes from a direct sum of flat tangles. So if you have any tangle like this, then you get a chain complex of geometric bimodules. And the usual notion that Kamanov studied is the homotopy category of bounded chain complexes of these geometric bimodules. In our case, we actually have to consider a variation of this, which is the homotopy category that we call K bar, Mn, of not necessarily bounded chain complexes, which again, I'll have to explain in just a minute why we have to consider the unbounded complexes. And so let me just kind of try to explain the idea of where these functors and natural transformations come from. So we're going to have functors. So for each group element in the Thompson group F, in this case, it's a, this is the general notation G, but in our case, it's the Thompson group F. So given an element of the Thompson group, we would like to define a functor that acts on this category. And then whenever we multiply them, we would like to define a natural transformation. Well, okay, so we're going to start with a chain complex, which is denoted A star in this definition. So it's a chain complex in, so there are n points on the bottom and then 2 to the k points on the top. So this is a chain complex of geometric bimodules in this category. And we also have an element G of the Thompson group. Well, from an element G, we have this construction theta sub k, which gives us a 2 to the k strand diagram. From that, we construct a tangle. And then we can apply the Kavanagh construction to construct the Kavanagh chain complex. And this is what's denoted by C star of theta sub k of G. So again, from a group element, we get a strand diagram, then a tangle, then we take a Kavanagh chain complex, and that's our C star of theta sub k of G. And we also have any chain complex A star in this homotopy category of unbounded chain complexes. And we just take a tensor product. In other words, we just take our new tangle that we constructed and stick it on top of that chain complex. And taking the tensor product is precisely just sticking that chain complex, Kavanagh chain complex of our tangle on top of the given chain complex. So this is an analog of Kavanagh construction that he used for braid groups. But in our case, we don't have braids, we have these tangles that come from Thompson group elements. All right, so now how do we construct the natural transformations that correspond to multiplication in the Thompson group? And so this is also an illustration of the reason that this group action is lax as opposed to Ginian. So in Havanagh's case, he worked with braid group elements. And so if you have a braid group element acting on this given chain complex, then it's kind of an invertible action, because if you have a braid group element, then you can multiply it by the inverse on top, and this is going to be the kind of the inverse of the action. In this case, this is not the case. We get more general tangles. In general, it's going to be not invertible. And so what happens, as you recall, the way that the multiplication H times G is defined in the Thompson group is that, for G, you have a tangle, well, a strand diagram and then a tangle. For H, you have a strand diagram and a tangle. And when you multiply them, you stack the strand diagrams and then you reduce them. Okay, so the reduction, so let me just kind of indicate here. So given G and H, you can multiply them H times G. And the strand diagram that you get for the product is generally not going to be reduced. And so these are the reduction moves. Okay, so there's a cancel and caret, and then there's this type 2 move. The cancel and caret, if you think about what happens in terms of the Havana chain complex, is kind of very predictable. It's just you just create these sort of trivial circles. This is what happens when you apply the Tangle construction or the Jones construction of links from strand diagrams. So this is kind of very mild modification. What happens on the right for the type 2 move is quite drastic. And this is the illustration at the top here. So on the right, if you apply the Tangle construction to the picture on the right, you just get 4 strands. This is just an oriented version that I drew here. There are a couple of different oriented versions, but this is one of them. You just take 2 parallel copies of the vertical strands. What happens on the left is sort of more complicated, and this is the picture of the tangle that you get from the diagram on the left in the type 2 reduction. And what happens in this natural transformation that we assign in our construction is that there's a morphism in the category of Havana chain complexes, and this comes from the settle cobordism. So there is a tangle on the left, and then there is a tangle on the right, and then there is a tangle, and then there is a settle cobordism connecting them, and the rectangle across the interval. And there is actually a non-trivial proposition that if you have a sequence of these type 2 reductions that are these type 2 moves on the right, there is a kind of a well-defined composition. So it does not matter in which order you do these type 2 moves. And this proposition actually does not work if you consider both type 1 and type 2 moves. So type 1 move is here on the left when you create a trivial circle. And it turns out that if you use both of them, then it's not a necessarily unique composition, that if you do it in different orders, you might get different cobordisms. But if you only do settle cobordisms and type 2 reductions, there is a unique composition that's independent of the order of these type 2 reductions. And so we apply the sort of the chain map that's associated in Havana theory to this unique composition of settle cobordisms, and this is our natural transformation P sub h g between the composition of the 2 functors P sub h and P sub g, and going to the functor P associated to the product h times g. And let me just conclude by saying that earlier in this talk, I mentioned that we have a symplectic faithfulness result for tangles. So if you have 2 Thompson group elements, say G and H, then for sufficiently large K, you'll have the tangles that you get are going to be distinct, that are associated to these 2 group elements. And what we're working on right now, we expect this to be true, that if you have 2 group elements, J and H in a Thompson group, we expect that their action is going to be different asymptotically on this category. So there is a parameter here, which is the number of endpoints on the top and the bottom of these tangles. We can choose that, and we expect that asymptotically, for sufficiently large K, these 2 group elements will have different actions on this category that we constructed. And I'm going to end here. Thank you.
So, can I ask you a question?
Sure.
So first of all, hi Slava, it's been a long time.
Hello, Scott.
So the Thompson group is this quirky group, really quirky group, right? Like it's a really interesting group. And so is one of your goals to maybe prove some of the conjectures about the Thompson group using sort of Jones polynomial or Havana?